Okay, so did you get the email from Google Classroom that there's a new assignment posted? I hope you did. Yes, okay, thank you. All right, so as you can see on that, it is due on Friday, 4th December. One more thing I wanted to talk about, let me wait till everybody is here. Well, just maybe remind me. So the thing is on Saturday, I checked my calendar and I have another meeting from 4 to 5. So what should we do? Should we go with 3 to 4? Does that work for people? Let me just double check. There is a meeting from 28th November from 4 to 5. So how would 3 to 4 work with everybody? Is that okay? Okay, Saraswati, Mukesh, Somnath. Thank you, Somnath. Mukesh? All right, well, okay, thank you. All right, so let me just, well, anyway, we'll come back to this. All right, recall what we're doing. We're talking a little bit about characteristic functions. So analytically, these are nothing but Fourier transforms of measures. And they're useful because they help you do many things. And one of them is prove the central limit theorem. So last time we saw a few things about what does it mean for a complex valued function on a measure space to be measurable. How do you do integration with complex valued functions, etc. And then what we did is we started talking about this characteristic function. So let me go ahead and turn off the video and share the iPad screen with you. All right, so here's just a very quick reminder of what's going on. Let x be a real valued random variable on omega fp. Then the characteristic function phi equals phi x of x is the mapping phi taking the real line to the complex plane, defined by phi of theta is expectation e to the I theta x. Okay, and of course that means this is expectation cosine theta x plus I times expectation sine theta x. Now, one thing I want to point out is that, and actually we made a note of it last time, note that phi is defined for all theta in R. And I want to say that this is the case no matter what random variable you're taking, okay? So remember, you have seen random variables like Cauchy random variable for which the mean is infinite, right? You may have seen some other random variables where the mean is finite, but the second moment is infinite. Well, and of course, with moment generating functions, you have seen that the existence, the domain of the moment generating function is somehow connected to integrability, to existence of moments. But the thing with characteristic function is it is defined for all random variables for all theta. Okay, so I just want to mention, note that phi is defined for all theta in R, for all real valued random variable x. Okay, so you do not run into that same issue of, oh, the random variable is not integrable, so its moment generating function doesn't exist. Well, that doesn't happen for characteristic functions. Okay. Next thing we did is we started making a list of certain important properties of characteristic functions. So we said let x be a random variable with characteristic function phi. Then we have the following things. We have phi of 0 is 1. We checked this last time. Then we have absolute value of phi of theta less than or equal to 1 for all theta in R. We checked this last time as well, and this basically came from this property. Absolute value of the integral is less than or equal to integral of the absolute value. The third property, number C here, is the following. The function theta mapped to phi theta is continuous on R. So let's see why this is true. Okay, so let theta be a real number. What do we want to do? We want to show that phi is continuous at theta. So now in this case, it'll be very helpful to use a sequential characterization of continuity. You know that a function is continuous at a point, theta, if and only if for every sequence theta n which converges to theta, the value of the function at theta n converges to the value of the function at theta. So we'll use that characterization of continuity. So let theta n going from 1 to infinity, be any sequence in the real line such that theta n converges to theta. If we can show that phi of theta n converges to phi of theta, then our job is done. All right, now this is going to be quite straightforward. So let's look at phi of theta n. What is this? This is expectation e to the I theta n x, and phi of theta is expectation e to the I theta x. Now, you can start to smell what's going to happen, right? As n goes to infinity, theta n converges to theta. So I theta and x should converge to I theta x, which means e to the I theta and x should converge to e to the I theta x. So maybe the expectation of e to the I theta and x should converge to expectation e to the I theta x. To do the last step, you will need bounded convergence or dominated convergence or something like that. But now you see the path to proving this. Okay. So for every omega and omega, we have e to the I theta and x omega converges to e to the I theta x omega. Remember, this is just fixed, okay, for any omega. And I, of course, is fixed. So if theta n goes to theta, then this exponential goes to that exponential. All right, so now you start to think, now let me just think in terms of Lebesgue dominated convergence theorem, because you know that the bounded convergence theorem is a special case of that, right? Okay, so now I'm starting to think in terms of Lebesgue dominated convergence theorem. I have a sequence of measurable functions converging to a limit. When is it true that the limit of the expectations is expectation of the limit? So you know that a sufficient condition is if the sequence of functions is dominated by an integrable function, and that is easily obtained here. Right, so you look at absolute value of e to the I theta and x omega. Well, this is just 1. Right? That means if I take the absolute value of this guy, this is just always 1. All right, so now you remind yourself that you have this Lebesgue dominated convergence theorem even for complex valued functions. If fn converges to f almost everywhere, and if there exists a non-negative g in L1 such that absolute value of fn less than or equal to g almost everywhere, then f is integrable, and integral f is limit n goes to infinity integral fn. So now you just use the dominated convergence theorem to complete the proof. So by Lebesgue dominated convergence theorem, e to the I theta x is integrable. Actually, there's nothing of value here. You already knew this. Okay, you already knew that e to the I theta x is integrable no matter what x is. But dominated convergence certainly gives you this thing which you did not know. Okay, expectation e to the I theta x is limit n goes to infinity expectation e to the I theta n x. So that is just saying that phi theta is the limit n goes to infinity phi of theta n. In other words, phi of theta n converges to phi theta as n goes to infinity. In other words, phi is continuous at theta. All right, now what's the next property? The next property says that the characteristic function of minus x is just the characteristic function of x complex conjugate. All right. Or more precisely, the characteristic function of minus x evaluated at theta is just the complex conjugate of the characteristic function of x evaluated at theta. Here, basically for z and c, I may use one of these two notations. Of course, it's very standard, right? I may use z bar or z star as complex conjugate. Okay, this is quite straightforward, right? So phi minus x of theta is expectation e to the I theta times minus x. Now I can write this out using Euler's formula as expectation cosine theta x minus I times expectation sine theta x. And now you say real number minus I times a real number is just complex conjugate of a real number plus I times real number. In other words, this is just complex conjugate of phi x of theta. Then there is this last property. This says, suppose I'm taking a phi of ax plus b. Now here a and b are real constants. Okay, maybe I should say that. Let me just sneak in a note. Okay. So if I have real constants a and b, and I take ax plus b and I take its characteristic function, what I'm going to get is I'm going to get e to the I b theta times phi x of a theta. Right? This is true for all real constants a and b. Again, this is a very straightforward check. So phi of ax plus b of theta is expectation e to the I theta ax plus b. So this is expectation e to the I theta ax times e to the I theta b. Now remember that e to the I theta b is a constant, and so I can pull it out. So I pull out e to the I theta b, and I'll have expectation e to the I theta ax. But wait, what is this? This is simply phi x evaluated at a theta, and so you get e to the I theta b times phi x evaluated at a theta. Any questions so far? All right. Now, I said that characteristic functions are a useful tool when you want to prove something like the central limit theorem. Why is it a useful tool? Okay, so the answer to that question is kind of given by this particular thing, this lemma that you see up here. Now, okay, remember when you talk of central limit theorems, as we've said before, a central limit theorem is a type of theorem. Okay, so there is no one central limit theorem. It is a limit theorem which has a certain flavor to it. Now, when you study central limit theorems, the very first situation you look at is you look at a situation where I have x1, x2, and so on. Hang on. Excuse me. Right, you look at a situation where you have x1, x2, dot, 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 which are all independent and identically distributed. Now, later on, once you become a master of this basic central limit theorem, you may try and extend it to more general cases where the random variables may fail to be independent. But anyway, when you start from the basics, you start with the case where the random variables are independent. And one of the nice things is that if I take a sum of independent random variables, then the characteristic function of the sum is just the product of the individual characteristic functions. And this helps you go a long way in proving central limit theorem. Okay, maybe not a long way, but this is an important idea you use when you prove central limit theorem. So I want to make this observation here. It's not rocket science. If x1, x2, dot, 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 up to xn are independent random variables. Note, nobody's saying anything about identically distributed. Nobody's saying anything about integrable, nothing. Okay, if x1 through xn are independent random variables, and we set Sn to be the sum xi, I going from 1 to n, then the characteristic function of Sn evaluated at theta is simply the product k going from 1 through n of the characteristic function of xk evaluated at theta, and this is true for all theta in R. Okay, so characteristic function of the sum is the product of the individual characteristic functions. Of course, the requirement is that the xk's are independent. All right, so it's quite easy to check. This basically relies on this idea that you have seen many times. Independence means multiply. If I take a product of independent random variables and I take the expectation, then I could have just taken the expectation first and then taken the product, I would get the same thing. So that's what we'll do here. So let theta be in R. Phi Sn, of course, now I don't need to tell you, sometimes I'm writing phi. Well, when there's only one random variable in town and there is no danger of confusion, I may just write phi. When there are multiple random variables floating around and I want to specify which random variable it is that I'm speaking of, I may write phi subscript x. So similarly, when you see phi Sn, you should know, okay, this characteristic function of Sn. By the way, before I go any further, let's look at this review lecture thingy. And let's change it from 3 to 4 p.m. 3 to 4 p.m. Okay. So note the change from the earlier choice of meeting time. All right, anyway, I just wanted to remind you that when there are multiple random variables, we may indicate by subscripts which random variable's characteristic function is being referred to. Okay, so phi Sn of theta is what? Well, by definition, that's the expectation e to the I theta Sn. No rocket science there. Then so this is expectation e to the I theta summation xk, k going from 1 to n. Why is this true? This is just true by definition of what Sn is. Then I will use laws of exponents. If I take exponential of a sum, that is just the product of the exponential. So this is exponential product k going from 1 to n, e to the I theta xk. And now is where you use independence. So far, we have not used independence. Up to this line, we have not used independence. Now is where we use independence. So we'll basically say that for k going from 1 through n, these terms are all independent. The first term is e to the I theta x1, second term is e to the I theta x2, dot, 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 and all these terms are independent. And you know that expectation of a product of independent things is just the product of the expectations, assuming, of course, both sides are finite. That is a given. But anyway, by independence, what you get is you get product k going from 1 through n, expectation e to the I theta xk. Well, this is just product k going from 1 to n, phi xk of theta. All right, so when you're adding independent random variables and taking the characteristic function, that is just the product of the individual characteristic functions. Any questions with this? All right, so now I think we should at least look at a couple of examples. All right, so here are a couple of examples. So suppose x takes values in just +1, -1, with p of x equals 1 equals p of x equals -1 equals 1/2. So basically, you can think of this as a coin flip. So if you want, you can say that head corresponds to 1 and tail corresponds to -1, or vice versa, depending on whatever makes you happy. And then you can calculate phi theta. This is expectation e to the I theta x. So this is e to the I theta times 1/2 plus e to the minus I theta times 1/2, and this ends up just being cosine of theta. All right. Now let's look at the case when you have a Poisson random variable. So suppose x is Poisson with parameter lambda, or lambda is greater than 0. Now you remember what a Poisson random variable is, right? So x takes values in z plus, and the probability that x equals k is e to the minus lambda, lambda to the k over k factorial for any k in z plus. Now characteristic function definition is the same. So characteristic function is phi of theta is expectation e to the I theta x. Now you remember how to take expectation. So this is just going to be the sum k going from 0 to infinity, e to the I theta k, times the probability mass function evaluated at k, which is e to the minus lambda, lambda to the k over k factorial. And now, of course, this e to the minus lambda you can pull out. And then I'll have sum k going from 0 to infinity, lambda e to the I theta, the whole thing to the k over k factorial. And now you remember that this is the series expansion for exponentials, no matter whether you're taking the exponential of a real number or a complex number, right? You know that sum k going from 0 to infinity, z to the k over k factorial, this is how you take e to the z, and this holds regardless of whether z is real or complex. And so, of course, this quantity right here is e to the lambda, e to the I theta. There's an e to the minus lambda here, and so you get e to the lambda, e to the I theta minus 1. All right, so the next thing I want to do is I want to look at an example, another example, which is the normal random variable. Okay, so suppose x is n01. Okay, so we claim that phi of theta is e to the minus theta squared over 2. So let's see how you do this. Okay, now I'm a little tempted. So there's this nice book by Duret. Okay, and I think perhaps he likes to make fun of people. He likes to make fun of physicists also. Anyway, he shows how you calculate the characteristic function of a normal random variable, and he gives what he calls a physics proof. And he calls it a physics proof because it's not really rigorous. And then he gives a math proof, and this is basically his math proof. But anyway, let me, since I have spoken about physics proofs, let me say a little bit about what this guy Duret does in what he calls quote unquote a physics proof. Okay, so this is physics proof, and this is in the book by Duret. This part I took from Duret. I haven't been referring to Duret much, but anyway, he basically shows you how from a physics proof you can guess that the answer is going to be this. But then, of course, the physics proof is not rigorous, as you will see momentarily. And so you need to do something else to convince yourself that the answer you got is in fact correct. Okay, so here's the formal calculation. So I have x is n01. Okay, so let theta be in R. Right? Then I'll take expectation e to the I theta x. This is going to be what? This is going to be the integral over r, 1 over square root of 2 pi e to the I theta x, then e to the minus x squared over 2. And then I'll have e to the minus theta squared over 2, e to the plus theta squared over 2. Right? And one second, what do I get here? E to the minus theta squared over 2. Okay. One second, why am I getting something that looks funny here? Have I done this correctly? I think I have expectation e to the I theta x is integral over r 1 over square root of 2 pi. Okay, integral over r 1 over root 2 pi. Right. Okay, so I'll have 1 over, okay. I'll have 1 over root 2 pi e to the minus x squared over 2. Then my integrand is e to the I theta x. And then I'll multiply by e to the minus theta squared over 2, e to the theta squared over 2. So that's just keeping the value the same, dx. Then what I'm going to do is I'm going to take, this is the integral over r. This is going to be the integral over r, 1 over root 2 pi e to the minus 1/2 x squared minus 2 theta x plus theta squared. I think I have made a mistake here, by the way. Let me just double check. I think maybe the answer should be e to the theta squared over 2, not e to the minus theta squared over 2. Oh, you know, it is e to the minus theta squared over 2. Where am I going wrong then? Just a second, guys. That's very strange. Okay. And then you have e to the theta squared over 2 dx. Okay, so I'm obviously doing this wrong. Okay, so as you can see, I'm bungling up even the physics proof, right, as it is called. Okay, anyway, there is some formal calculation you can do, and you can basically make yourself believe that it should be e to the minus theta squared over 2. The point is he does something like this, and then he says, oh, this is e to the theta squared over 2 integral over r 1 over root 2 pi e to the minus, oh, I see what I have done wrong. Okay. I completed the squares wrong. Here's what I made. Here's my mistake. Actually, I know what I did wrong. Anyway, you guys with me so far up to this point? Okay, then I will use this fact. I squared is minus 1. Remember that there is an I here. So you need to keep that in account when you're trying to complete the squares. So this is going to be the integral over r, 1 over root 2 pi, e to the I theta x, e to the minus x squared over 2, e to the I squared theta squared over 2, e to the minus I squared theta squared over 2 dx. Okay, so now we'll get it. All right, so now what I'll do is I'll take e to the I squared theta squared over 2, I'll pull that out, and then inside the integral, I'll have the integral over r, 1 over square root of 2 pi, and then I'll have e to the minus 1/2, and then I'll have x squared minus 2 theta minus 2 I theta x plus I squared theta squared dx. Any questions so far? So this is where I was making a mistake when I was completing the squares. The thing is, you have to keep in mind that Here you have x squared over 2, and here you have I theta x. So when you're completing the squares, you should have I squared theta squared over 2 and minus I squared theta squared over 2. All right, so then you say, well, this is e to the, well, I squared is minus 1, so minus theta squared over 2, the integral over r, 1 over root 2 pi. And then you'll say this is e to the minus x minus I theta squared over 2 dx. Okay, and then you do something, well, at least I am extremely uncomfortable with doing this. You say, oh, this is integral over the whole real line, 1 over square root of 2 pi e to the minus variable squared over 2 dx. So this thing is 1. Okay, so that's, I think, why he calls it a physics proof. Okay, so 1. Let me not say hopefully, let me say perhaps. And if that is correct, then your answer should be e to the minus theta squared over 2. But anyway, this is not a rigorous proof, but this kind of helps you sniff out what the correct answer is. Now let's do a math proof and check that it is actually correct. The math proof may be less enlightening, but at least it's rigorous. Okay. Any questions with what I'm babbling about? Okay, so let's do this for the normal random variable. So let's suppose x is n01. So I want to find phi theta as expectation e to the I theta x. So this is the integral e to the I theta x 1 over square root of 2 pi e to the minus x squared over 2 dx. This is something you know. Okay, now what I'll do is I'll take e to the I theta x and I'll use Euler's formula. So I'll have integral cosine theta x 1 over root 2 pi e to the minus x squared over 2 dx plus I times integral sine theta x 1 over root 2 pi e to the minus x squared over 2 dx. Then I'll stare at this term and I'll realize that this is going to be 0. Right? Remember, sine is bounded. Okay, so there's going to be no integrability issues at all. Sine is an odd function. This is an even function. The whole thing is an odd function. So this integral is going to be 0. So what are you left with? So thus, phi of theta is the integral of cosine theta x 2 pi to the minus 1/2 e to the minus x squared over 2 dx. So now what this guy Dirac does, the way he proves it, is he goes ahead and finds a differential equation for phi. And then that differential equation is sufficiently easy that he knows what the unique solution is. And so he says, oh, if phi solves this differential equation, then phi must be this function. And that's the route we're going to take. Well, now if I have to take this and take derivatives, I should justify that I can actually differentiate under the integral sign. But you can. I'm not going to justify. So differentiating both sides, this can be justified. You get phi prime theta is the integral of minus x sine theta x 2 pi to the minus 1/2 e to the minus x squared over 2 dx. And remember here on the right side, inside here, we have differentiated with respect to theta. Okay, not x. So derivative is going to be minus sine theta x times x. Okay, next I'll leave it to you. Well, I said I'll leave it to you, but I'm actually doing it. Next thing you'll do is you'll integrate by parts. Okay, so you'll take u to be 2 pi to the minus 1/2 sine theta x. You'll take dv to be minus x e to the minus x squared over 2 dx. You'll find what du is. You'll find what v is. And lo and behold, you'll get, remember, you took phi prime theta and you had an integral on the right side. So phi prime theta is still on the left, but the integral on the right side has now been calculated using integration by parts. So you get 2 pi to the minus 1/2 sine theta x e to the minus x squared over 2 from minus infinity to infinity minus this integral. Then you reason that sine theta x is between minus 1 and 1. As x goes to infinity and x goes to minus infinity, this term is going to go to 0. Only this term will survive. And then you say, hey, wait a second. I have minus theta here, and this thing inside here is nothing but phi theta. So what do you get? You get that phi prime theta is minus theta phi theta. And so you get that phi prime theta plus theta phi theta equals 0. And this is one of the easiest differential equations you know how to solve, right? This is a first order linear ODE. And so, I don't know. I always call this method of integrating factors, but I don't know if that is correct. I think it is integrating factors. Anyway, you basically want to multiply both sides by something, such that using the product rule, the left side is the product, is the derivative of a product. So here you do phi prime theta e to the theta squared over 2 plus theta e to the theta squared over 2 phi theta equals 0. Now you stare at the left side and you realize that this is nothing but d d theta of the product. Well, if d d theta of this product is 0, then you know that the product must be constant. So phi theta e to the theta squared over 2 must be constant, which means it must take the same value for all theta. Now, for theta equals 0, you get phi 0 e to the 0, which you know as 1, and so you get that phi theta must be e to the minus theta squared over 2. Any questions with this? Now, I want to just give you another thing, which I want to just leave it, do it yourself. I want you to figure out how to do this. Find phi y of theta. And I'll give you a hint. You don't have to go through this tedious calculation. There's a quicker trick to do it. I'll leave it to you to think about that. All right, so now next I want to just state without proof this particular result. And one of the things this result does is it basically tells you that a probability measure is uniquely characterized by its characteristic function. Now, at some level, this probably doesn't surprise you because you have learned when you studied Fourier transforms that you can go back and forth between a function and its Fourier transform. Right? You've learned something along those lines. You start with the function, take its Fourier transform, then you take the inverse Fourier transform, you come back to the function. So it should not surprise you that something like this should hold, and it does hold. So here are the questions we're asking and the answers we have. Let x be a real valued random variable with CDF, capital F, law mu, and characteristic function phi theta is expectation e to the I theta x. Okay, now remember, as soon as I give you capital F, you know the law mu. Equivalently, if I give you the law mu, you know what the CDF is. Okay, now we've said every random variable has a characteristic function. And now the question is this: if we know phi, is there any way to reconstruct capital F? That's one question. Second question is if F and G are CDFs, okay, and a priori you don't know whether they're the same or different. Okay? But you happen to know that their characteristic functions agree on the whole real line. Is it true that F equals G? And the answer ends up being yes. Okay, so this thing I want to just briefly go over. This is a theorem. Unfortunately, we won't be able to go through the proof in its entirety. So this is so-called Levy's inversion formula. So this says, suppose x is a real valued random variable with CDF, capital F, law mu, and characteristic function phi theta equals expectation e to the I theta x. Then for a less than b, you have limit t goes to infinity 1 over 2 pi integral minus t to d e to the minus I theta a minus e to the minus I theta b over I theta times phi theta d theta is 1/2 mu of the singleton of a plus mu of the open interval ab plus 1/2 mu of the singleton of b. Okay, and now you remind yourself how you calculate probabilities of individual points, and you can check that you get 1/2 fb plus fb minus 1/2 fa plus fa minus. Okay, and here's a further claim, which again will not prove. If the integral over r of absolute value of phi theta d theta is less than infinity, in other words, if the characteristic function is integrable, okay? If the characteristic function is integrable, then x has a PDF, and that is actually a continuous function. Then x has continuous PDF small f, which is given by this formula. And again, this is no surprise to you. This reminds you of Fourier transforms, inverse Fourier transforms, right? And you know that in different books, the convention they use is different, right? In Fourier transforms, different books put the minus sign in different places, right? Some guys put it when you're taking the forward Fourier transform and not when you take the inverse. Other people do it vice versa. Then in some books, you will see this 1 over 2 pi in the inverse transform, but not in the forward transform. In other books, they will break it up as 1 over root 2 pi and put it in both of them. Anyway, so modulo those variations, you see that f is just the Fourier transform. No. Inverse Fourier transform of phi. Any questions with this? All right, so now I just want to say a few more things about the type of convergence that you have in the central limit theorem. So the type of convergence one has in the central limit theorem is something called convergence in distribution. Okay, so now your first question will be, well, what is convergence in distribution? All right, so now the thing is, you look at different books, they'll basically start with one definition and then they will find a whole large number of equivalent ways to say the same thing. So let's see if we can do it in one shot, okay? So below I will list several ways to define convergence in distribution. For real valued random variables, they are all equivalent. So let's just say let x be a real valued random variable on omega fp with law mu and CDF, capital F. Let x, okay, then I will do the following. For n greater than or equal to 1, let xn be a real valued random variable on omega n, fn, pn with law mu n CDF fn. Okay, so one of the things that should just leap out at you right now is that you can see that I'm allowing the possibility that x is defined on this probability space omega fp, x1 is defined on the probability space omega 1 f1 p1, x2 is defined on the probability space omega 2 f2 p2, dot dot dot. In general, xn is defined on the probability space omega n fn pn. In other words, it may be that not all random variables are defined on the same probability space. I mean, if they're defined on the same probability space, it doesn't hurt, okay? That doesn't hurt at all, but I'm just saying that that is not required. So not all random variables may be defined on the same probability space. Okay. So the following are all equivalent. Okay, so the first one is the following. Fn of x converges to f of x as n goes to infinity for every x in R, which is a continuity point of f. Okay, basically, in the end, I'm going to say that all these statements basically mean convergence in distribution. So what is the first description of convergence in distribution I'm giving? Fn of x should converge to f of x as n goes to infinity, not necessarily for all real numbers, by the way, not necessarily for all real numbers, but only for every real number x in R, which is a continuity point of f. Now, you know what a continuity point of f means. This means that i.e. f of x equals f of x minus. Right, so that's what a continuity point means. Because remember, actually, let me do the following. Continuity point means f of x plus must equal f of x must equal f of x minus. But remember that this first equality is always true because our CDF is right continuous. All right, so first way to say convergence in distribution is that fn of x converges to f of x as n goes to infinity for every x in R, which is a continuity point of f. Another way to say that is the following. Probability that xn, no, here I should say Pn xn less than or equal to x converges to P of x less than or equal to x as n goes to infinity for every x in R such that P of x equals small x equals 0. Okay, now I hope I don't have to explain much how I got 2, right? The idea is that this thing on the left is simply fn of x. And this thing on the right is simply f of x. So it's basically saying that fn of x should converge to f of x as n goes to infinity for every x real such that p of x equals x is 0. And now you remind yourself, wait a second. P of x equals x is simply f of x minus f of x minus. All right, so that's another way to say xn converges to, well, we have not yet stated that, but we'll come to that. Number 3, Pn of A converges to P of A as n goes to infinity for every Borel set A with probability of x belonging to the boundary of A is 0. Okay, now you can see that this is just a slight variation of number 2. I'm not saying that it's very easy to prove. I mean, okay, it's not very difficult to prove, but you can prove this. But what I'm saying is you can see that this is a slight variation of properties 1 and 2. Basically, you're saying that if you're, right, so here is the thing, right? Your first instinct may be that xn converges to x if for any set A, Pn of A converges to, oh, no, this is not correct. Sorry. Remember, the A's live on the real line. So P of Pn of xn in A converges to P of x in A. Yeah, this is correct. Okay. So as you can see that if you look at this, you can see that the second property is a special case of the third one, right? In the second one, in the third one, the second one is obtained when you take A equals minus infinity x. Okay. So 3 is basically a generalization of 2. So this is another way to say it. Now, as you can see, this type of thing kind of uses the CDFs. And now, if you're talking about random variables in a general metric space, then what does CDF mean, right? So anyway, there is another way to say this, which kind of helps you in a very abstract setting. For every bounded continuous f taking R to R, we have limit n goes to infinity En of f of xn equals E of f of x. Okay, now remember that there is an n here because the probability measure is Pn. So since the probability measure changes with n, the expectation operator changes with n. All right, so these are a couple of different ways to say the same thing. And what are we going to say? So, Okay, so if any of these things hold, then that is by definition xn converges to xn distribution. Another way of saying that would be to say that um, mu n converges to mu weakly. And a third way to say the same thing would be that Fn, the CDF, converges to F weakly. All right. Any questions so far? I'm not really expecting you to be able to digest too much of this at such short notice and in such a such a short amount of time. Okay, now I just want to mention the following. Let's take a different color here. Let's go with green. So 3 can be written it can be written as mu n of A converges to mu A as n goes to infinity dot 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 dot. I don't want to write this whole clause again, okay? For every Borel set A such that, let me write it. For every A in the Borel sigma algebra on R with mu of the boundary of A is 0. Okay, so of course the number 3 can be, number 3 was written in terms of the probability of X falling in a Borel set. Of course, that is the same as saying that the law of X hitting that Borel set. Okay. So these are a couple of different ways of saying a convergence in distribution. One of the things I want to bring your attention to is the following. In convergence in distribution, we are never, ever comparing xn and x pointwise. Here's what I mean. What was in convergence almost surely, what was the requirement? The requirement was that P of the set of all omega in omega such that limit n goes to infinity, xn omega equals x omega is 1. Right? This was convergence almost surely. So what were you doing here? For individual omegas, you were comparing xn of omega and x of omega. Right? And what you wanted was, you wanted that limit n goes to infinity, absolute value of xn omega minus x omega goes to 0. That's what you wanted. So in convergence almost surely, for individual omegas, you were comparing xn and x. Then what you wanted is that the absolute value of xn omega minus x omega as n goes to infinity should go to 0. And this should happen for almost all omega. If that is done, then you have convergence almost surely. So you are comparing xn and x at individual omegas. Now, of course, if you have to compare xn and x at individual omegas, they have to be defined on the same probability space. Right? Just as if I tell you f, what the hell? Okay, if I tell you that f is a function taking 0, 1 to r, and g is a function taking 2, 3 to r, then to talk of the function f minus g, this is meaningless. If the domain of f is 0, 1 and the domain of g is 2, 3, how can I even talk about f minus g? That would be meaningless. So in order to talk about f minus g, f and g should be defined on the, should have a common domain. In convergence and probability, what are we doing? So we're looking at the probability of the set of all omega in omega such that absolute value of xn omega minus x omega is greater than epsilon. And again, what are we doing? We're at individual omegas, we're comparing xn omega minus x, we're comparing xn omega and x omega. And we want the probability of this set to go to 0 as n goes to infinity. So again, we're comparing xn and x at individual omega. So what you want here is you want for every Okay, so note that in convergence and distribution, we do not do a pointwise comparison of xn and x. Moreover, in fact, if x and x are defined on different probability spaces, not only are we not doing a pointwise comparison, we cannot do a pointwise comparison. Right, and again, why is that the case? I will just refer you to this. If f takes 0, 1 to r and g takes 2, 3 to r, to talk of f of x minus g of x is rubbish, right? Because, wait a second, now what is x in 0, 1 or x is in 2, 3? Okay, if this x is in 2, 3, then I should take y here. So anyway, another fact that I just want to mention is that convergence in distribution is weaker than both these guys. Convergence almost surely and convergence in probability both imply convergence in distribution. All right, so I think we are out of time there. So let me stop. And as I said, I would like to move the Saturday's lecture to 3 p.m. rather than 3:30 because I have another meeting at 4. Any questions? As I said, I will not be doing any new